Hello everyone. In this session, I'm going to give you a very quick overview of boosting and why really boosting is a very powerful machine learning mechanism. How can the boosting really improve the predictions that we are doing either for classification purpose or even in the numerical prediction? What is the role that boosting can play to improve the result that we are getting? So it's one of the most important supervised learning based mechanisms, just like your neural networks or support vector machines or decision trees or random forests. We can also look towards the usage of boosting as some kind of an enhancer for our prediction purposes. So here in this session I am not going to look at anything with respect to R or any tools per se. It's a very comprehensive session on the use of boosting in predictive analytics. So I'm going to talk about the basic introductory aspect and in general what is the criteria behind the boosting algorithms, how they really work, and what is the power of the boosting. So these are some of the things, very short session, but it should give you the first picture in terms of why do we really need to get into the boosting aspect. First thing, it's one of the most powerful supervised learning algorithms or learning mechanisms, especially when we are using it for the classification purpose, whether it is binary or multiple category or ordinal, whatever is the classification. This supervised learning based classification, which is the boosting, can be used quite comfortably. The way it works is it really looks at team effort, right? Probably the concept is it goes with the team building part. It combines the performance of many weak classifiers. So it takes the first classification that it does is still a weak classification, but it combines the performance of many weak classifications to really produce a powerful committee. So basically it believes in the concept that 1 plus 1 is not equal to 2, 1 plus 1 is greater than 2. So that's the typical fundamental. When two weak classifiers come together, the combination is going to be much more powerful than one strong classifier. So that's the basic intent behind the usage of boosting. It's very simple because it takes so many basic quick to use weak classifiers and tries to combine them to produce the desired result. So the process is very simple and even computationally inexpensive. So this is completely based on iteration. It keeps on doing the same thing again and again. So it has a lot of simple classification algorithms, right? It depends on simple classification algorithms, but apply that same algorithm again and again by changing the strategies in such a way that overall result is going to be a much better result. So the algorithm is not a purple algorithm, the classification is not a purple classification, but that simple classifications itself, it is applied n number of times on that data with some kind of an improvisation. So that's where it is an iterative process. So the solution is kept on improving until it gets a much better predictive result. So algorithm is focusing more and more on new strategies for classifying difficult observations. Some observations which cannot be classified correctly. So it focuses more on those observations. right? Probably one person is being classified as no diabetes, but that person is very high on diabetes. Now this is a wrong classification. Now what the algorithm does is it tries to give more weight to this observation so that this person gets classified into the diabetes category. So those observations that are getting very difficult for classification, they are given more and more weights. So the strategies that are implemented differ based on the observations that are getting classified versus the observations that are not. So that's the kind of internal learning that the mechanism is, the algorithm is doing before it gives any kind of the final solution. So when you look at the boosting algorithm, the first thing that happens is you give some training data to it. We train the model, we give a training data to it. The first thing that happens is the weights of that training data that you are supplying, they keep changing. So iteratively, the weights of those training data, each record in the training data, their weights, there are different weights that are applied to each observation in the training data, and that weight is iteratively changed. So the observations have different weights in different iterations. So because of that, what happens is the classifier will try to find a new solution in each iteration. So if I have given 5 observations as the training data, it does not give all of them the same weight. So each iteration, the observations are given different weights, and based on the weights that are given to this observation, it comes out with a solution which is S1. Again, the weights of each of these observations are changed, and again a model is fitted, and that fitted model, it goes with a solution S2. Like that, so many solutions it gets, a different solution for each combination of weights to the training data. And how is it able to get the high accuracy? So it looks at difficult observation, those observations that could not get classified properly as a part of solution 1. So it tries to increase the importance of them. When it comes to solution 2, those observations that could not get classified properly, their importance is getting increased. They are getting a much higher weightage in comparison with those observations which got classified correctly. So those observations which got classified correctly will receive a lesser weightage, and those observations which could not get classified properly, they will get a much higher weightage. So it's a kind of learning from experience, learning from the past mistake. So that the reweighting that is happening, the weights that are given to the observations, they keep changing, and the way they change is those observations which got difficult to classify, they will receive much more importance, which means the weightage that you are giving to those observations increases, and the weightage that you give to the observations which got classified correctly will typically go down. So that's an iterative process. And all the results now that we have got, they are combined into a prediction committee. Now we had 100 solutions with us. All those 100 solutions go into a prediction committee, and out of that 100 solutions we take the better performing solutions. Out of these 100 solutions that we have got, we look at the better performing solutions which have done the classification really well. Those weights are typically increased now. Now the next step that is going, now I have 100 solutions. Instead of giving equal weights to all the 100 solutions to come out with the final solution, I'll give more weights to those solutions which have done a better classification, And so there also iteration specific coefficient is typically coming up. And through that, the weights of those algorithms that have those iterations that have given better solutions, they are typically increased. So for each iteration, there is a specific coefficient that is coming up. And based on that entire process, the resulting weighted majority vote. Now it's a weighted voting because those which have done a higher classification, they will receive a much higher weightage compared to those which have done a poorer classification. So because of that reason, we are going with a weighted majority vote. It's not a plain majority vote, and based on that, the real classification is going to happen. Now, because of that reason, there is a good chance that the accuracy of the model can be much higher compared to the other algorithms. Again, it is never guaranteed that this is always the best. Probably we can try out with different data sets that we have tried till date using neural networks, support vector machines, etc. In some cases, we may get a much better result, but it may not be the case in all cases. So this is one more way. We need to understand how boosting is typically done so that we can apply it to our data in such a way that we may hope that the results may be much better. So the power wise, we simply look at it as an attempt to get much better predictive models and more satisfactory result. I should be able to do the prediction much comfortably. My result should be more and more better for prediction purposes. And for learning tasks where comprehensibility is not crucial. Now, here we already understand with respect to predictive models, there is always a trade-off between predictability and interpretability. So predictability, it may not be the case that all models which are good at predicting, they are interpretable easily, and those models which are good at interpretation, they may not be doing a good job with respect to predictability. When you are talking about something like neural networks, the interpreting and explaining the neural network could be a much complicated aspect. Whereas it might very well be possible that by using neural networks, I should be able to do the prediction of my data more comfortably. Whereas when you talk about a linear regression kind of a model or a logistic regression kind of a model, interpretation of the model is quite easier. But we are not sure whether we would be able to do the prediction to the core by using those kind of models in all cases. So wherever we are talking about interpretability or comprehensibility as not being crucial, I can very well rely on the voting methods. Even if you remember, random forests, random ferns also go with the concept of voting itself. Whereas let me tell you here, it is weighted voting. Because weights are differing across those classifiers based on how much of better classification they have done. Different solutions are given different kinds of weight based on what is the level of accuracy they have in their classification. So the target function is optimized and some kind of penalization is typically being absorbed, some kind of implicit penalization is being applied based on the number of boosting iterations as well. So we have to look at, with the minimal amount of boosting, what is the best kind of solution where the error is the least possible and the predictability of the model should be much higher. So that should be our target for all the exercises that we are going to take up. We are going to deal in sessions where we would be applying boosting for classification purposes, where our response variable is binary. We will look at multiple category cases. We will look at regression kind of case where we are doing a numerical prediction. where we also look at discrete numerical variable like Poisson regressions and etc. So we are going to look at even that aspect. We are also going to look at the survival model, where how I can use boosting in case of survival, and even where the response variable is ordinal. So we will be dealing with all these sessions, which we have done even in case of decision trees. So which means if I am dealing with the same data set, I have an option where I have an opportunity to do the comparison with the models like decision trees, neural networks, and see to what extent boosting has helped, at least in some cases, in terms of coming out with a much better prediction, right? So this is more from the perspective of the basic understanding of the concept of boosting, and this should really drive us in terms of using various boosting algorithms for the prediction purposes, whether it is for classification or for numerical prediction, right? So this is what I wanted to take up as a part of this session. If you have any further queries, you can get in touch with me by giving me a call on the number that you have given me, that I have given below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.